Hello everyone, hope you guys are doing well and enjoying lectures. In the previous lectures we discussed about basic concepts for flow networks. We discussed about Ford Fulkerson's algorithm and Edmond-Karp's algorithm, which are based on augmenting path approach. What is an augmented path? What are residual network? What is the capacity of along each edge in the residual network? These concepts we discussed in previous lectures. If you have not watched those lectures, I would recommend you to watch that. In this lecture, we're going to be discussing about push-relabel algorithms. So these are little different kind of algorithms for solving the flow network problem. What is a flow network problem? As in simple sense that we want to know what is the maximum flow value we can achieve in a given network or a given graph. So as you can see here in this example, it's a typical example we were discussing about the flow problem in previous lectures. Let's say you want to send some bags of rice from Bangalore to Toronto, and you have different possible routes available to you. And each route has a different capacity, means that you are allowed to send only limited number of bags. Say for example, from Bangalore to London, you can only send 13 bags maximum. So similarly, on each edge in this directed graph, you have capacity associated. And the goal is to find what is the maximum value of the flow, or how many maximum bags can you transfer from Bangalore to Toronto via different routes possible. So push and relabel, it's a very simple concept that you keep pushing the flow onto the edges and adjust the height of the vertex. Now what it means that you can think in terms of water flow network, like how the water is flowing in pipeline. So think about the edges as the pipes and the nodes or the vertex in the graph as the pipe joints. So what joint does? It just facilitates the distribution of the water along the different edges, and the condition is that it should not store any water, okay, or it should not, its excess flow should be zero, it should not overflow, okay. So that's the basic concept on which we're going to be working. Now as the water flows from higher altitude to lower altitude, you see, let's say water is flowing like that from a higher altitude to lower altitude. So that similar concept is applied here. Each vertex is associated with the height, okay, and from the higher altitude node, water will flow down to lower altitude node, okay. So let's say S, and then the lowest altitude would be the sink node, the T, okay. Now in the real world, water is flowing from the higher altitude to lower altitude always, but because it's just a concept, so we are kind of taking that idea from there, but it's not that the lower altitude cannot send to the higher altitude. Well, we're gonna maintain this property, but let's say so this is the conceptual framework. Think in terms of how the water is flowing, how the fluid is flowing in the fluid network, all right, and keep pushing the flow downhill, okay, towards the sink, and start from the source vertex. Here we are saying source vertex is Bangalore. So initialize the source vertex height with whatever number of vertices you have in the graph. So that will become the source vertices, vertex height, and the sink vertex, that is Toronto, its height would become 0, okay? Because that is the preliminary or initialization step we are forming here, that all the water is flowing between Bangalore to Toronto nodes. Okay, so let's conceptualize further what is an access flow. Access flow is nothing but whatever amount of the flow it is receiving into one node, and whatever amount of the flow is going out of the node. So let's say, for example, if it is receiving 10 and it is only transferring 5, so access flow would be 10 minus 5. Okay, now see, access flow is positive for this example, so it means that this node is overflowing. Okay, and since this node is overflowing, we need to adjust its flow. The condition is that we should achieve the 0 overflow. So it means that there should be no overflow. Okay, so let's say how, otherwise the algorithm is very simple, that you just initialize the graph once and keep doing the push and relabel operation until there is nothing, no more push and relabel operation left. That's a very simple algorithm. Now, what is the initialization step? Initialization step is very simple, that for each vertex you make the height and the access flow 0, and the source vertex height is the number of vertices in the graph. Okay, so that's the initialization step up to line number 1 to 6. Now from line number 7 to 9, what it is doing basically, so in this kind of algorithms, you work on a node. So you work on first node and then keep looking its adjacent vertices. Okay, so let's say initialize the node S, and we have many say edges going from S. Okay, so we gonna work on S first. So initialize all the adjacent edges and vertices of S, or in other words, saturate those edges. Means that if that edge has the capacity 10, so send the 10 flow value. That's the initialization step. Okay, and after doing the initialization, you will get first set of push and relabel operation. When you're going to execute push and relabel operation, you will identify more push and relabel operation in the whole graph, and you just keep on solving it, and in the end you will get the maximum flow value, right? Relabel operation is nothing but when the height of a vertex is low and the vertex is overflowing, means it has excess flow, then you adjust the height, you make its height higher than its neighbor vertex so that it can push the flow. And what is the push operation? It's nothing but when a vertex has excess flow, okay, then it can push that excess flow to its neighbor vertices. And how much flow value it can push, that is identified the delta value, which is at line number 3. So that much flow value it can push. Okay, so after performing the push and relabel operation, you will identify more operation, and that's how these algorithms work. Now let's take an example. Okay, for the convention purpose, the number before the slash on each edge level is representing flow value, that how much flow you are sending from one node to another node, and the another number after the slash on each edge label is representing capacity, means that how much maximum flow can you transfer from one node to another node. Okay, and I'm using one more convention here on each node, that number, first number, there are two numbers separated by semicolon. first number says the height or the label of each node, and second will say how much is the access flow on that node. Okay. Now we're going to be working on a residual graph. Okay. Those the residual graphs, the concept of these graphs with the residual flow value, residual capacity value, I have discussed in the previous lecture. Please watch the previous lecture if you are not familiar with residual graph in the context of flow network. Okay, so nevertheless, as you can see here, this is a same example, typical graph. What we did, we just initialized all flow to 0. Okay, except and now we're going to work on the source node. So as you can see, the source node has the height 6. As we said that we will give the height, initialize the height of source vertex to 6, which is equal to the number of vertices in the graph. Okay, or in a table you can see here that the node numbers. S is at a higher altitude, value 6. Okay, and what are the adjacent nodes to S, L and P, and those edges between S to P and S to L, we saturate these edges. Okay, saturate means we send the flow value equal to its capacity. So in terms of between S to L, we send the 13 value of the flow, which is equal to its capacity. Same way to another edge, which is flow value is 10 and capacity value is 10. So we did saturate these two adjacent edges of the source node. Okay, so now we got, see, relabel operation, because now here we have access flow value at node P 10, which is not 0. It means that it has some value of the fluid or water which it can transfer, but it is not able to transfer because it has the same height as its neighbor vertex L. So we increase its height or we relabel it. Okay, so after relabeling it, its height become 1, and as you can see, P, we moved to a higher altitude, and now P can easily transfer the access flow value. Okay, so it can transfer to L, but how much it can transfer? Well, what is the capacity here of the edge between P to L, which is 3. So maximum value it can transfer is 3. So let's do that. Let's push the access flow towards node L. And what is the resultant value? Resultant value at node L would be 16. Simply that 13, which was the access flow earlier on that node, and it got 3 more units of flow from node P. And what how much is left at node P? It's 10, which was the earlier flow value, minus 3, that is 7. Okay, that is left. Now as you can see here, the orange edges going backwards, these are residual graph edges, and we have the flow value 3, which is equal to how much we sent for maintaining the flow conservation. We discussed this concept in previous lectures. So here I'm not going to discuss it again, but as you can see here, this is the orange edges are extra edges in the residual graph. All right. Now you got another relabel operation because node L has access flow. It has to transfer. Okay. Now where it can transfer? It can transfer. It has 2 adjacent edges. One is going to T and one is going to F. All right. So now it can transfer to T. How much maximum? 7. 7 is the capacity. How much maximum it can transfer to F is 6. That is its capacity. So let's relabel first. We relabeled it, and as you can see here, we have now node L at a higher altitude than T and F, so it can safely transfer the excess fluid to F and T. And how much it will transfer depending upon the capacity. So it transferred 6 unit to F, and the excess flow at F becomes 6, and it transferred 7 units to T. Okay, that is our sink node. And how much is left at node L? That value is 3 units of flow or fluid is left at L. Okay, good. So far so good. Now we got some value at F which is greater than 0. So that is the excess fluid greater than 0, and this node is overflowing. So we got to relabel it, okay, because now F has the excess fluid or excess flow, but it cannot transfer because it has the same height as its neighbor vortex N. Okay, so let's adjust its height. New height becomes 1. Now as you can see here, as soon as we made its height 1, we are violating the flow between L to F. Now L cannot transfer the flow because both have same height, so we need to increase the height of L, or we need to relabel the L. So let's do relabeling of L. We did relabeling of L, and L moved to the height 2. Now what happened here? We again disturbed the flow conservation between L and P. So now P cannot transfer the fluid to L, so we need to adjust the height between P and L. Okay, but before that, the L now has the higher height. It will just push backwards the excess flow, which is 3 to P. Okay, now it pushed back the flow, and you see the P, it has original excess flow. Now we again have to adjust the height of the P, because it has to transfer its excess flow. Where it will transfer? There is only one node L where it can transfer. Okay, so we need to adjust it. We adjust relabel and push. After relabeling and push operation, as we can see here, 3 is nothing but the height of the node L, which is 2 plus 1. So we made its height greater than the height of the node L, so that it can push the flow from P to L. Okay, but again now L has the excess flow of 3 units, because the edge between L to T and L to F are both saturated. No more flow can go, so only flow can go, or it will not take the flow from P, means it will push back. So we need to relabel L and push back the flow. We relabeled L, and how much we're going to relabel? We just need to make its height greater than the height of the P. Okay, so let's do relabel and push back. So it pushed back the 3 units of flow to P, and now P has excess flow. We do the same thing. We relabel and push, and then L got extra fluid, and then we relabel and push again. And now here, as you can see, we relabel and push again. And now this is quite interesting here. So as soon as we relabel P, its height becomes greater than the height of source vertex if there is a edge connectivity between S to P. So what it means that now P has higher height. It can say to S, okay, it's not able to receive more fluid. Okay, so it will only receive 3 units of flow, which it can safely transfer to L. Okay, now and 7 units of flow will send it back to the source vertex. All right, so again because L cannot take now the extra fluid 3 units, so it will try to push it back. So we relabel and push operation at L. And now see, as soon as we relabel, so the previous label was 6, and now new label would be 7 plus 1, which is 8, and 8 is greater than the height of the S. So what's going to happen now? It will receive the flow from the P, but extra flow it will push it back to the source. Okay, it push it back to the source, so only 10 units it will take. Okay, so now see, the excess flow is 0 at L, excess flow is 0 at P, so no more relabel and push at L and P. Now we focus on the other node, which is F, okay, and N. Okay? These two more nodes are left. So if we do that, then we push the extra flow, which is 6 units at F, to node N. Okay, as F has higher height, we can safely push it. We pushed it. Now how much we can push? What is the capacity of the edge between F and N? And we pushed it. Now N has extra flow, so we need to relabel its height or increase its height, adjust its height, so that it can push the excess flow to T, which is our anyway the sink node. So we adjusted its height, okay, and now we can push it. So we push the flow, but how much we can push? Whatever is the capacity. Capacity is 5, but it had excess flow of 6 unit, so one unit of excess flow is left at N. So what it will do? It has no more edge where it can transfer that fluid. So what it will do? It will push it back to F, that I'm done, I cannot take any more units, you see. So that's how, think about that, you are sending the bags of rice from Frankfurt to New York, and the flight says, no more guys, I cannot take more. Okay, or let's say from New York to Toronto, your flight only can take 5 bags. Okay, so what's going to happen? It cannot, New York station, or cannot store the bag of rice. So what it will do? It will push it back. It will say to Frankfurt, no, I cannot keep it. You keep it with at your location. So it will push it back. Okay, so we need to relabel and push it back. So we relabeled it and pushed back. Okay, so as you can see here, that new height of the node N is 2. Okay, and we pushed back one extra excess flow unit back to the F node. Okay, now F node will say, I cannot store that extra 1 bag of rice. So what need to be done? We need to adjust its height. Okay, I'm the boss now, I'm sending it, back and forth, that operation keep on doing. So F, relabel and push, we increased its height and pushed it back to N. N says the same thing, I cannot take it, I'm the boss now, so we increase its height and push it back. F says, no boss, I'm the boss, you keep it. So we increase the height of the F, or make the F as a boss, and boss sends the extra bag to N. Okay, N says, no, I cannot keep it. We do the same operation, relabel and push. Okay, now F says, no more, I don't have any more capacity left, and I cannot store, I'm the boss now. So increase its height and send it back, relabel and push. Again, relabel and push. Now again, relabel and push. Okay, so see here, as soon as we relabel and make its height 7, earlier height was 7, 1, but if we wanna make F as a boss, we need to have its height greater than the height of the N, means new height would be 8 plus 1, which is 9. Okay, so as soon as the new height comes, then F is the boss of L as well. It means, or in other words, F has higher height than L as well, so it will push back that 1 bag of extra rice to L. Okay, it's the boss now, so it pushed back the 1 bag of extra rice to L. Now L cannot store that extra bag of rice, So what L gonna do? Now L has the higher, L is at a higher altitude, okay, than its neighbor from where it was receiving the flow, which is S. So it will simply push back 1 unit of bag or 1 unit of flow to S, okay. So it will just simply push back. And as you can see here that if you see the heights or altitude of different vortices, you can see in this table, okay. And finally this algorithm completes. And what is the flow value here? Say how much maximum flow? Maximum flow is 9, which is going from S to L, and 3 value, which is going from S to P. So that much, 12, would be the maximum flow value. All right. So now, as you can see, we have solved this flow network problem using push and relabel algorithm, generic approach. How about its time complexity? Well, it turns out to be that it is in the order of v square multiplied by e, number of edges in the graph, and v is the number of vertices in the graph. So v square multiplied by e. Thank you very much, guys. Thank you for liking and subscribing LeProfesseur on YouTube.